I'm Chris.
Fernando.
Sean.
So we're working on a digital nervous system. We've been working on this for about a year now. So the brain is really plastic. There's three fundamental things we need to talk about to understand the context of the project we did. There's the parallelization versus serialization sort of concept here. So the computers that you typically use and compute with are using serial computation. And so with that, you're working on, they compute one thing at a time. So if you use the analogy, parallel works at multiple things at once. So the analogy you can use to kind of understand this conceptually is if you had one person reading a book, or if you split the book into, lots of people read one page of the book at once. So there's a mismatch here because the brain actually works much like a parallel computer, with each neuron actually working as a independent unit of computation, and so they're all processing independently. So by neural networks, you're going to simulate large networks of a large enough biological proportion. The hardware is commercially available, power efficient, parallelized, and reconfigurable. Reconfigurability is important here because where you can still have a typical computer, the ones you probably have on your desk right now, you can have it work on this and work in a parallel method through multi-threading. It's not effective. The architecture on the engineering of the hardware itself, there's just a mismatch. It's going to be slower. And so the context of the project is that a lot of neuroscientists want to use the FPGAs and the neuromorphic hardware because it's faster and it's more efficient and effective in a lot of ways. And so what we wanted to do, but no one knows how to code parallel languages. It's just much more difficult. Many of you probably didn't even know that there was the distinction between the two. So the whole concept of ours is to create this router, this translation, this bridge between when we code on serial computation and we want to code on FPGA, which is a normal hardware. So as I was saying earlier, the brain's highly integrated and parallel, so there's just mismatch. I'm going to move this a little bit. And then so we're going to move on to how the software works.
So on the software, we want to model the biological neuron, using the leaky integrate and fire. And so this model is very simplified, so it doesn't take into account all of the dynamic complexities of a neuron, like all the different ion channels and how that would impact the activity of the neuron. So we are using the LAF model because it's very computationally efficient, and so we can scale out one neuron into just thousands and thousands of these neurons to understand how the population of neurons or a simple brain area in the brain functions and how the activity affects how people feel or people think. And so just basically how information flows in the neuron is that you have the circle, the neuron, receiving some sort of input, some sort of weighted input, and then in the neuron, all of those inputs are summed and compared to a threshold membrane potential. And if that total membrane potential exceeds that threshold, then a spike is generated in an all or nothing fashion. Okay, so once we have that one neuron defined, we want to extrapolate into a network of n neurons. And in this example, you can see all the different 5 circles of neurons with each connection leading from one neuron to another. And we can represent that in a matrix form, which is much easier to computate in Python and MATLAB. And just the zeros, or if that neuron is not connected, and it has a weight of W if it is connected.
So much like the software component of it, okay, cool. We have the hardware component in this case being the FPGA device. The FPGA device is actually this little chip called the Spartan 6. And what it really is just a block of memory. And what happened there is that a graduate student in the lab, Bruno, actually used a hardware programming language called Verilog, steep learning curve, and configured this so-called state machines that are very similar to how the neural processing works. So how Chris discussed, there's this sort of presynaptic process where you have a set of input stimuli coming from any surrounding neuron that's connected to this one neuron. Then they're again, accumulated through some summation, done those integrated, and then from there compared to some once you're in the cell body, compared to some threshold. Similar process again, you get some threshold in there. All the variables are stored in this one block of information. And then from there, if the threshold is exceeded, you have a spike event, which is then routed to this one so-called routing table, which connects the neuron and the axon to another neuron, wherever it's been, anywhere in the device has been connected. So to sort of visualize this for more grand scale of things, what Will was trying to mention is this whole idea of parallel processing. In this case, you have 4 individual cores, so you can run individual neurons at each core simultaneously, as opposed to say a serial process where you would only have 1 core, and each neuron would have to run, sequentially. So in this case, you would then program the neuron, and this one were to spike, routes it over to this one here, the cell body process spikes, routes it to wherever else it's connected, and it continues this whole process for as long as you would like. The difference between the Spartan 6, this FPGA device, and your computers, your personal PCs, is the real-time operation. That's one of the things. It's that we can actually run this bunch of neurons at a 1 millisecond time scale. And 2, it's a more important part of the distributed memory. So in this case, is that each neuron actually has access to some memory device, which can then allow it to update itself, as opposed to your computers right now that you only have 1 block of RAM. And if a neuron, say, population of 1,000 wants to update, each one is going to have to go individually into the RAM, pick up the information, do the processing. So you start creating, it becomes more of a queue, less of this everyone goes in simultaneously, which is ineffective in terms of the processing time. So again, features, memory is distributed faster, and then the hardware architecture matches the actual biological processing. So our hypotheses and aims.
Okay. So basically, what we gathered from all this background information is that the hardware does not match how the brain functions. Basically, so we can run our simulation on a computer, a serial computer, a consumer computer, but it just won't match the same speed, and it'll be harder for neuroscientists to actually run their hypotheses. So we said that let's use a neuromorphic hardware. Let's use an FPGA that's more parallel, as Will mentioned. So then we can easily run our simulation and be able to gather as much data and results as quickly as possible.
I mean, to sort of bring an analogy to, again, we've been keeping discussing this like this, there's this sort of incongruence between the processing which is parallel on your computer device, computational device, which is serial. You think of, for example, if you're a native speaker, say my native tongue is Spanish, and you try to pick up a new language, there's going to be some time for you to develop a sentence as opposed to a native speaker. So in that sense, your language, considering that to be the software, has some incongruence with how your neural architecture is working. But the beauty about biology is that over time you keep practicing, your neural architecture will start shifting and eventually, match the language, but then enable you to speak a lot faster. So the problem here is that your computers can't do that. They can't reconfigure themselves to match the process. These devices can. So exploring that domain.
So just part of our design was we started with the software where we described the network, we set up the neuron model, and then we sent all that information to the hardware, to the parallelized hardware to be able to run the simulation. So the first step, of course, is to set up the software simulation. And to do that, going back to what I said, was we define the neuron model, we define how that neuron receives input, and define where that neuron sends its information to.
And the beauty about Python is just how easy it is to configure that.
Yeah, only a couple of lines of code, and we already have a functioning neural network. Yeah. And so, if you look at number 2, the next part is actually running the simulation. And as Fernando mentioned, it's very easy, very simple, very intuitive to run the simulation. One of the first things we have to do is define the time step. And you can think of that as seconds on a clock, where a neuron can only function at that exact second. And so this sort of sets a temporal resolution in that a neuron can never send or not send a spike before that millisecond or before that second. And that also could lead to an overestimation of synchrony, just because the neuron will always fire at a periodic interval instead of maybe half a millisecond. And then the second step would be define the total runtime as how long the simulation runs, and we send the run command and just let it do its own work.
So similarly, how we designed the hardware implementation, we wanted to use the very similar structure as the previous language we were using, which was actually a module in Python called Brian. In this case, develop a function where you first have to configure the number of cores you want to use in this case. So for this example, we wanted to say 4 cores, and per core you want to specify how many neurons you want to use. In this case, we said 256. So that's right there. You establish the parameters of your hardware. And then afterwards, once the parameters of your hardware have been established, you want to start parameterizing your actual model. So our hardware is already pre-configured to run an LIF neuron. So then you have to go in, get the weights, store them in the appropriate area, parameterize the actual cell body, which is giving the neuron parameters like the threshold, if there's any lead, refractory periods, when it spikes, where do you want it to reset, and then the routing table. I think how do you want your network to be connected. So same thing, you just establish a neuron group within a single core, give it its parameters, and again, the code handles all this configuration because it's not this straightforward. Then if you want to connect them, you just need to source target. How is everything related to? How is the information flowing amongst groups? And here's the output. I'm still working on actually reinterpreting the output, but this is actually how it looks when you're acquiring from the device. It's a 64-bit message, and what you need to do is chop it up into blocks, convert that from binary to decimal, and it's a matter of it's like you looking up addresses on a book. If you want to find out what's saying, it's actually more like looking up definitions. So it's creating a wrapper to reinterpret this, which under development. But the same process again, how you run it, just give you a runtime that you want it. It just runs on your device, spits out this information, and you have to reinterpret it. Same thing with the software. It should be looking at the software output.
So basically, we've already defined the neuron, the network, we've run it on the hardware, but what do we do with the end result? What do we get? We have a large data set of the spike times for each neuron, so whenever we get a certain time point whenever the neuron fires, and we can compile that into a histogram, this thing over here, where it shows the number of neurons firing in a certain time frame. And then from that, we can gather 3 different metrics for how similar 2 networks are. And that would be the ISI distance, spike distance, and spike synchrony. And that basically just shows how one network oscillates between a similar or a dissimilar phase compared to the source network. And this sort of relates to how we were trying to understand the population dynamics, because we're not interested in just one neuron, we're interested in how a whole bunch of neurons are firing and with respect to one another and with respect to other areas of the brain. So this oscillation could be translated to, let's say, how one brain area transmits its information to another brain area, and that leads to a whole cascade of information being propagated throughout the brain. This is just another metric that we can use to understand how one network influences another. It's a simple heat map where the darker color shows a more correlated connection between one network to another. And you can clearly see that this one has darker purple there. So this one has a higher correlation as opposed to this one.
Okay, cool. So conclusion, for our project, we have achieved some progress, many goals, but still need a little bit added to our project. So basically, we developed an open source functional system that connect the artificial brain to the machine. It's like a brain-machine interface, and we also proved the feasibility of using commercially available FPGA boards for our spiking neural network simulation. And but other things like we have to or we need to do is indicate the situations where it is optimal to simulate on CPU or it's better on FPGA. And last thing is like provide interpretable results from FPGA like some histograms or develop some visualization tool for that. And here's some future perspective of our project. One thing can be added to our interface. We can change different parameters and parameter strengths so that we can compare the resulting simulation with actual biological neural network. So our design can also further be developed to provide tools that grant access to the FPGA's pre-configured framework and to accommodate more complex SNN simulation on multiple FPGA boards, because our current design focuses on just single FPGA core chip with one chip. So the design is very limited to simulate just very simplified biological properties on a particular FPGA board. And once our interface are added with more channels, different parameters, our system can run multiple FPGA chips and be used to study more complicated neural network dynamics. It can be developed to brain-machine interface that can be used on other devices like Brainstorm in another lab in Stanford University. And our design will help neuroscientists and students now have the ability to investigate the dynamics of a parallel system without extensive knowledge of neuromorphic hardware. Our design can lead to greater progress through extensive hypothesis testing and prototyping. So many future medical applications and experiments about this design can be done in fields of neural processes and artificial biological neural networks. For example, as you can see from the above figure, it's an experiment in London to implant electrodes directly on the nerves and applying the brain-machine interface to achieve the goal that the process can be controlled by brain signals. Another example you can see on the right is a model and a simulation tool for creating a neuroprosthetic device, the neurochip. Neurochip simulation can replace one or more biological neural components in the brain with enhanced silicon chip. So to some extent, it is also neural processes. Simulation and modeling include artificial neural networks on chips to replace and so applications like these two examples above can keep improving our study as the bigger goal to do the study of human brain. And lastly, we'd like to.
So we didn't do the whole funding page. I guess $2,300 would be good. But everything's open source. So the whole idea is that you can buy this stuff like off the web, and you can use our code and start compiling this stuff. But yeah, the ultimate goal of this whole technology is to start developing reconfigurable hardware, in the sense that, for example, you can say this room, if it were to be reconfigurable to match, say, climate changes, during the summer it'd be a certain configuration, winter is a different configuration, as to optimize the temperature in the room. That's not something you see in engineering right now. Everything's static. Everything's, once you buy it, that's the thing you buy, and it's going to stay that for indefinitely. So if you think that idea is pretty cool, $2,300. And yeah, I guess lastly, just definitely thank Dr. Wheeler, Taryn, Ismail for putting this course together, because I know it's a lot of work getting a bunch of projects for all of you. it's hell. And also just our advisor, Fred, Sadiq, and Bruno. So Fred and Sadiq were on the software end, doing all teaching us all the theory in terms of how to design neural networks, spiky neural networks, different from artificial. And then I was working closely with Bruno. He's the one that actually designed the framework for the FPGA device, and I had to read all this Verilog code to translate over to Python and translate over to a nice little function. He was definitely his just comments on the code was great. Everything he really, if it wasn't for him, I would have not had anything with the hardware. But yeah, that's about it. Sorry for taking so long.